Welcome to Introduction to Soils Part 2, Soil Properties and Soil Health. In the previous lecture, we talked about what soils are and what they are made of, how soils develop, and how geologic and human history have shaped Vermont soils. In this lecture, we're going to take the next step and talk about soil development processes and how those result in observable soil properties. We'll talk about some of the key physical, chemical, and biological soil properties and discuss how these properties influence soil health. In the last lecture, we discussed different processes and factors that shape soil development. All of these processes that act on soil give rise to different soil properties, which can be loosely grouped into physical, chemical, and biological properties. In reality, there's a lot of overlap between these categories. Soil properties, in turn, shape the health of a soil, which is shown in this diagram. There are many important soil properties which we will cover in much greater depth throughout this class, but I wanted to give a brief overview of some of the properties that I think are key for understanding soil health. We are not going to talk about all of the properties important for soil health today, but we'll get into some of the big ones, and you'll learn more about other soil properties throughout this class. Color is one of the most readily observable soil properties. Color by itself doesn't necessarily influence soil health, but color can tell us a lot about what's going on in the soil that may affect soil health. Darker soil colors near the surface typically indicate organic matter accumulation, which is a natural part of soil development and is also great for soil health. Light colors in the soil can happen when a lot of chemicals have been lost through leaching, or they can be due to salt accumulation or light-colored parent materials. We have a lot of old forest soils in Vermont that have lost a lot of chemical compounds in the upper subsoil through leaching. So this light color in the middle of a profile is something you might see. Blue-gray colors in a soil can indicate that it is waterlogged. This can happen due to seasonal high water tables or compaction, often a combination of both, and you'll often see these blue-gray colors mixed with red colors in our very wet soils in Vermont. The gray color comes from reduced iron, and the red color comes from oxidized iron. So that mixture of colors is telling you that moisture is fluctuating in the soil, causing iron to cycle between its reduced and oxidized form. We typically don't see a ton of very red soils in Vermont, but if you did see one, that's often indicative of old soils with lots of weathering and accumulation of oxidized iron, and that's something more typically seen in the tropics. Another important physical property of soil is its texture. Soil mineral particles can be divided into sand, silt, and clay, depending on how small they are, and the balance of differently sized particles determines soil texture. The soil textural triangle, shown here at the right, tells us the texture of a soil based on the percent of sand, silt, and clay particles. Structure is a related soil physical property. As soil development proceeds, soil particles form aggregates that are basically mineral fragments glued together by sticky soil organic matter, as well as iron oxides or other cementing agents. Different soil structures are shown in the diagram at the bottom of the slide. Both soil texture and structure are shaped by the parent material a soil is made from, as much as how much it has weathered. Structure can also be strongly influenced by management, as lots of tillage can break up soil structure and cause compaction. Tillage can also cause losses of the organic matter that holds aggregates together, which will further affect soil structure. Both soil structure and texture affect key soil properties, particularly those related to water, including soil porosity, water holding capacity, aeration, drainage. And texture also influences soil cation exchange capacity, which we'll get into in a little bit. Some of the key chemical properties of soil are pH and cation exchange capacity. pH refers to how acidic or basic a soil is. Acidic soils are typically associated with a highly leached condition where soils have lost a lot of their more basic cations. If soils are acidic enough, aluminum can be soluble in its cation form, which is often toxic to plants. So high soil acidity can be a real concern for soil health. Soils that are more alkaline tend to be less leached and still have a lot of the base cations, things like calcium, magnesium, and potassium. Alkaline soils can also have a high concentration of salts, which is less good for soil health. In terms of chemistry, we also care about nutrient concentrations in a soil, particularly the plant's essential nutrients like calcium, potassium, magnesium, and iron. Soil chemical composition is influenced by many different factors, including soil parent material, how much it is weathered, which will result in acid production and eventually leaching of nutrients, and then also how a soil is being managed, particularly with respect to amendments that influence pH and nutrient content. Cation exchange capacity reflects a soil's ability to store ionic nutrients such as calcium. Most soils are negatively charged because of the presence of clay minerals and soil organic matter, and so they are electrostatically attracted to nutrients that are cations, so nutrients that have a positive charge. The cation exchange capacity of a given soil depends on how many and what type of clay minerals are present, as well as the amount of soil organic matter. Cation exchange capacity can also depend on pH. The diagram on the right shows the cation exchange capacity associated with different soil textures and soil mineralogies. You can see that soil humus, or organic matter, has a really high cation exchange capacity, meaning that soils with a lot of organic matter can store and exchange relatively more plant nutrients. And finally, some of the key soil biological properties include soil organic matter content and soil biodiversity. Soil organic matter content refers to how much of the soil is made up of organic matter. You might remember from our last lecture that about 5 to 10% of any given soil is made up of organic matter. That number may be small, but relatively small variations in the amount of soil organic matter can have an outsized influence on soil function, because soil organic matter is so important in determining nutrient availability. Remember, it has a very high cation exchange capacity. And soil organic matter is also very important in driving soil aggregation. Soil organic matter is literally what glues soil aggregates together, so organic matter content influences soil structure, aeration, nutrient retention, water holding capacity, and more. Soil organic matter is most strongly influenced by biology and management. When there's a lot of living plants and active biology, soil organic matter will accumulate naturally. Tilling soils allows organic matter to be oxidized because they're exposed to air, which results in the loss of soil organic matter. Another incredibly important soil property is soil biodiversity, and this refers to biodiversity at all scales of life. Microbes like bacteria, fungi, and archaea are responsible for many soil nutrient cycling processes, especially for plant essential elements like nitrogen and phosphorus. But soil organisms of all sizes contribute to organic matter decomposition and cycling, so we really care about everything that lives in soils, including plants, arthropods, nematodes, and protozoa. As you probably picked up on, soil properties are complex, and many soil properties will influence other properties, making it really hard to examine any one property by itself. Soil health sits at the nexus of soil physical, chemical, and biological properties, and soil health is influenced by all of these categories of properties. What is a healthy soil? There are a lot of definitions of soil health out there. I personally like the definition used by the USDA Natural Resources Conservation Service, which defines soil health as the continued capacity of the soil to function as a vital living ecosystem that sustains plants, animals, and humans. That down a little further and think about what functions allow a soil to sustain life. I really like this list of healthy soil functions that comes from the Cornell Comprehensive Assessment of Soil Health Manual. In this framework, healthy soils retain and cycle nutrients that support plant growth. They sequester carbon, allow water infiltration, and facilitate water storage and filtration. They suppress pests, diseases, and weeds, detoxify harmful chemicals, and support food, feed, fiber, and fuel production. To know if a soil is healthy, we get to come back to our soil properties. Soil properties are our toolbox for understanding soil health. Some properties can be assessed visually out in the field, while others require laboratory measurements. Some key properties of healthy soils include good aggregation and structure with a lack of compaction, sufficient water storage and drainage, sufficient supply of nutrients, but not excess nutrients that can be pollutants, a large population of beneficial organisms ranging from worms to bacteria, and low weed and pathogen pressure. There are many properties that tell us something about soil health. Properties that are particularly easy to measure and are sensitive to variations in climate or management and can tell us something meaningful about changes in soil functions are all considered to be soil health indicators. So these are our best properties for understanding soil health and potentially how soil health may be changing in a particular area. And just in case you're not sick of seeing this diagram yet, let's look one more time at soil physical, chemical, and biological properties. While there's no definitive list of what the soil health indicators are, there are some commonly used assessment frameworks. In this version of the diagram, the soil health indicators that can be easily assessed in the field and are used in the NRCS in-field soil health assessment are shown in the bold text. These include properties like soil structure, aggregation, compaction, organic matter, and biodiversity. The indicators shown in italic text are included in the Cornell Comprehensive Assessment of Soil Health, which is one of the more widely used soil health tests that includes many different laboratory tests. So this can tell us about things related to soil health that we can't necessarily see with our eyes out in the field. Some of these properties that they measure include texture, pH, nutrient content, and soil respiration rates. Many soil health related properties aren't included in these assessment methods, and they're still important, but they may be more difficult to measure, they may be difficult to compare between soils, or they may not be as sensitive to changes in the environment or management as these other properties shown in italic or bold text. Throughout this class, you'll be learning a ton more about the science behind soil health, how we can assess it, and how to manage soils in order to build and improve soil health. Before wrapping up this introductory lecture, I want to leave you with a few reminders and caveats to keep in mind throughout this class. First of all, soils are complex systems that are influenced by many different factors and change throughout time. All landscapes and farms are different, and there is no silver bullet prescription to build soil health. What works in one production context, climate, or soil type may not work exactly the same in another. Any product or practice that sounds too good to be true probably is. There is no secret formula or one secret trick to healthy soils. What we do have is a solid set of soil health principles that can help guide management decisions, and you'll be learning all about the soil health management principles throughout this class. Building soil health is a long-term adaptive process. Multiple management practices can work in synergy with one another, and it will often require experimentation and adjustment to figure out the practices that work well together on any particular farm. Coming in with an attitude of curiosity and willingness to learn and adjust as you go is going to help you a lot on your soil health journey. Thank you so much for listening. I hope that these lectures helped you learn a little bit about soils and will provide you with a good foundation for the rest of the soil health course. Good luck.